Hey everybody, thanks for visiting me once again. Although I wish I could see your faces and allow you to ask questions right here, right now. But anyways, how much experience do you guys have in the laboratory? Do you have some experience with what we call a titration or an acid-base reaction? I don't know. Everyone's coming from a different space, different place. Here are some common definitions of acids and bases. The most common definitions. The easiest one that we might go with for right this minute is called the Arrhenius definition. An acid is anything that produces H plus ion in the water, aqueous in the water, and the base is anything that produces OH minus in the water. A more flexible, broad definition is the Bronsted-Lowry or the Lewis definition of an acid being a proton donor. You'll notice that is a proton, and the Bronsted-Lowry definition is a base is any proton acceptor. And lastly, the Lewis definition, Gilbert-Lewis, an acid is an electron pair acceptor, and a base is an electron pair donor. Yeah, these are very, very broad right here. And so the Lewis definition will be used in organic chemistry extensively, a lot. But we're usually just going to go with this definition. And as this is an introduction, we'll see more acid-base reactions in the second semester of chemistry. But for right now, we'll just go with this first definition, probably. The classic strong acid, strong base net ionic equation, where I only list the ions reacting, and that would be the acid, that would be the base, that would be the water. A lot of times I'll write water, HOH, to emphasize that the H plus is attracted to the OH minus, and they just form up like that, bond together, but of course it's H2O, it's water, liquid. Here's a few molecular and also net ionic equations for acids and bases. Maybe the most common, hydrochloric acid and sodium hydroxide. So 1-to-1 ratio. Sodium chloride is the salt, HOH is the water, acid, base, salt, water. But the salt doesn't necessarily have to be table salt, almost never is. This is table salt, but it's a coincidence that I chose sodium and chlorine. Could be iron and iodide, anything. Well, almost. Anyways, then that's the H plus and that's the OH minus. The chloride here cancels the chloride here, and the sodium here cancels the sodium here. Although I was too lazy to write the total ionics so you can see that easily. My bad. Here's another one. Nitric acid. 2 nitric acid units and 1 barium hydroxide unit, because there's 2 OHs there, react to give barium nitrate. That's the salt, and water again. But the barium, the barium's a spectator floating in the water before and after. The nitrate's a spectator floating in the water before and after. They cancel. And I have 2 H's and 2 OH's giving 2 waters, but that all divides by 2 to give me my, once again, simple net ionic equation. Same story would be true for this one, although I didn't write it out, but maybe I shoulda, coulda, woulda. Here's the chloric acid, and it's a strong acid, so I could write this. Lithium hydroxide is a strong base, so I could write this. And again, the net ionic would be the same. But what if I wanted to know something about titrating, slowly adding one compound into another? Yeah, can I shrink that down? Dang it all. Let's see. So how do I make that smaller? Let me just close this window. There we go. If I Google images for titrations, I see things like this. Yeah, things like this. Where I always have a burette. Yeah, I always have a tall, skinny burette holding the water, the titrant, and I titrate into these flasks, slowly and carefully adding one known amount to the unknown amount. Usually this is the unknown, usually this is the known, but it doesn't have to be that way. It could be backwards. And I carefully measure how much stuff from the burette I add to my known volume of the unknown, and slowly, carefully titrating to find out relative volumes and concentrations. I should know the volume and concentration of one and the volume of the other, but not the molarity or vice versa. So yeah, all right. Anyways, let's see, where was I at? Oh yeah. So here's my molarity and volume of one acid, and the molarity is unknown for the base. I have the volume of the base though. So since it's 1-to-1, it's really simple. If it's 1-to-1, it's M1V1 equals M2V2, or acid and base. MAVA equals MBVB, and solve for the unknown. This one times this one divided by this one. Just about that easy. Here's a weak acid and a strong base, but as long as one of them's strong, it could be a strong acid or it could be a strong base. That's usually all we'll consider is a strong interaction or reaction. I only have a one-way arrow. If both of them are weak, then I got a pretty big problem where I'm trying to decide how much they'll go to the right, and that's a huge pain in the backside for us, so we're going to skip that. But here's a strong base, cesium hydroxide, reacting with phosphoric acid, kind of a weak acid. But you'll see again, I know molarity and volume of a certain acid or base, and I only know the molarity or volume of the other one. So what? What's up with that 3? So I got to take this more slowly. It's not 1-to-1. I can't just no-brain it. So I take the molarity times volume of the first acid to get the moles, or I didn't get rid of millis, so I still have millimoles of the acid. So I have millimoles of this, but then I notice a 3 there, so I better carefully say, let's see, 3 moles of base react with 1 mole of acid. 1 mole of acid, 3 moles of base. Put the moles of the acid on the bottom so they cancel, discovering 3 times 3.22 moles of base. Then I can take it with that molarity, 0.375 moles per liter, and I could use the moles per liter as a conversion factor, or I could straight up divide moles by molarity. Millimoles by molarity gives milliliters, or millimoles times liters over moles gives, again, milliliters. So that's the volume of the unknown base, the unknown volume of the known concentration of base. Well, I don't know how this is sitting with you. I wish I could see you scrunching your eyebrows or shaking your head yes, but I'll just go on for now. Here's another example. Hydriodic acid, lithium hydroxide, strong acid, strong base. I have some acid and I have some base. And they told me the molarity and the volume for both of them. So you know what? Maybe I'll write it like this. I really only care about the reactants. I could talk about that in a minute. Maybe I will, but I'm just worried about this not being the right amount to use. 50 times 1.1 is 55 millimoles, milliliters, millimoles. 37.8 milliliters times 1.24 molarity is 46.9 millimole, milliliter, millimole. So some texts actually introduce a table, something like this in the beginning of the book, but our book doesn't even introduce it until next term, I think. But in the beginning, I had therefore 55 milliliters of this, millimoles, and 46, almost 47 millimoles of this. Well, guess what? It's a strong reaction. It goes one way, you see, one way. So it's going to consume as much as it can, and I'll take all the 46.9 millimoles of this and react with 46.9 millimoles of this. So this goes down by 46.9. This also goes down by 46.9 to nothing, but I still have a little bit of this left over. Isn't 55 more than 46.9? So guess what? I call this one excess, and I call this one limiting. If I had a little bit more of this, if I had, 8.1 millimoles more of this, up to 55 millimoles of this, then it would react with 55 millimoles of that. The question could be then, almost to end with, is what's the final concentration of acid? Well, I had 8.8 millimoles excess, so that extra is still floating in the water. But if you'll look back up here, I had 50 milliliters of acid and 37.8 milliliters of base. So my total volume is really the sum of those two. What's that, 87.8? So 8.1 millimoles divided by 87.8 milliliters comes out to the ending molarity, the final molarity of the acid left over. All right, we could include the products in that same story. Of course, I'm doing it in water, so when I say no water here, I'm really thinking of no water having had come from this reaction. So in the beginning, I mix this and don't have any of that. But this goes down, and this goes down, and this goes up, and this goes up, because these are products being produced, 1, 1, 1, 1. And of course, I made almost 47 millimoles additional of water, but I already had so much water floating in. 80 some milliliters of water is quite a number of moles of water. So I'm only making a teeny bit more additional water, but and it's not really that much of a concern. But my real interest was in the leftover acid in the water, not having enough base to cancel it. Should we try one more of these silly things? At least one more. What volume of 0.521 molar acid is needed to titrate 40 milliliters of 0.657 molar ammonia NH3 water? Ammonia is a very famous weak base. Oops, sorry about that. Ammonia is the most famous weak base. HNO3 is the strong acid, nitric acid. So it goes one way, weak base, strong acid. This H plus grabs onto the lone pair on the nitrogen. Maybe I should have, could have, would have written that, but I didn't. In any case, transfer of a proton. The nitrate is actually in the water before and after. So I really should cancel it as a spectator if I want to write a net ionic equation. And I did. That nitrate cancels this nitrate. And, oh yeah, I had 0.521 molar acid and 0.657 molar base, 40 milliliters of it. Since it's a 1-to-1 ratio, very nice, very easy. One of these, this one times this one divided by this one would give me my volume of acid to use. Just about too simple. If it's 1-to-1, it's almost a no-brainer, as long as you know the simple rule to go through. In other words, millimoles of base, millimoles of acid. All right, one more. One more. I hope just one more. Two more. I lied. Oxalic acid is actually a solid, and it's used to standardize or know exactly what the concentration of a base is. I take 3.471 grams of it. You can weigh it out very accurately. It's very dry and very consistent. And I use that to titrate with the base. The base takes 47.25 milliliters of the aqueous solution to neutralize that acid. So paying attention to sig figs, what's the concentration? What's a molar square bracket concentration of sodium hydroxide? Nice to know that the 2 H's, 2 carbons, and 4 O's add up to 90.03 grams per mole. Let me rephrase that in an equation. So oxalic acid and sodium hydroxide. But you'll notice it's a 2-to-1 ratio, 2 of these to 1 of these. And, well, I don't know. Let me go ahead and change this grams to moles. See how many moles of acid I have. So 3.471 grams of oxalic to moles of oxalic. Then I say, aha, 2 moles of NaOH for every 1 mole of acid. Did a little conversion there. 2 moles to 1 mole. So that's actually 0.07710. That 8 is not significant. I mean, doesn't count as significant in the end. I had 4 sig figs in the beginning. I'll save 4 in the end, but I don't want to round too soon. Or I might lose something in rounding. And so that's, so I brought that number down again. Now at this point, I could change my milliliters to liters or my moles to millimoles, but I should have, get rid of the milli or keep the milli, let it cancel, either way. So that's 77.10.11 millimoles. And the volume of the base was 47.25 milliliters, and the millis cancel, and I'm left with a straight up molarity of the NaOH. Interesting. I know the first time you see this, it's like, that's insane. I'll never be able to do that. But you can, and you will, if you practice. Lastly, arsenic acid. I think this arsenic or arsenic. I think this is arsenic acid. It's a triprotic acid, so 3 hydrogens. And this is a diprotic base, strontium hydroxide. You'll notice a 2-to-3 ratio. That's a salt. That's water. So I have a molarity and volume here. So why don't I just multiply those? 37.1 milliliters times 0.115 molar gives me a millimoles of strontium hydroxide. Then I better use the balanced equation, 2 to 3 to cancel. Cancel the strontium hydroxide and convert it to the acid, 2-to-3 ratio, and that gives me my moles or millimoles of acid. And lastly, I'll just take the millimoles of acid and divide them by the milliliters. We said 50 milliliters. We said 50? Yeah, we said 50 right there, 50. And that will give me the molarity of the acid. Oh, goodness gracious. Thanks, guys, for watching. Feel free to ask questions in class, after class, during office hours. I'd love to see you.